Good morning, afternoon, evening, everyone, and welcome to today's webinar on reactive pyrolysis applications for polymer and additive analysis. My name is Asti Damayanti, and I'll be your moderator for this event. We're excited to have you all join us from different parts of the world. Today, we'll be exploring the innovative applications of reactive pyrolysis, a powerful analytical technique that's making significant advancements in polymer and additive analysis. Before we get started, here are a few important notes. This session will last about 1 hour. Dr. Karthikeyan Satrugnan will present the first part, and afterward, we'll have a dedicated Q&A sessions. So please feel free to type any questions you have into the chat box at the bottom right of your screen as we go along. A recording of the webinar will be sent to you afterward via email. Now, it's my pleasure to introduce our speaker, Dr. Karthikeyan Satrugnan, who is the Regional Technical Manager at Frontier Laboratories. Dr. Satrugnan has extensive experience in advanced materials characterization and is an expert in pyrolysis GCMS technologies. He'll be sharing with us insights on how reactive pyrolysis is applied in the analysis of polymer and additives. Without further ado, Dr. Satrugnan, the floor is yours.
Thank you, Asti. So I really appreciate your short introduction, also welcoming the participants on behalf of Frontier Laboratories. And hello, everyone. Good afternoon to the Asian participants and good morning to the European participants. So it's really great to see you all again remotely or online to share some of our applications with the pyrolysis GCMS. And I hope you will have some new learnings or new sharing through this session. And like Asti mentioned, please feel free to put your questions in the chat box, so which we can address at the end. Let me share my screen first. Okay. I hope you all, Asti, can you confirm the screen is visible to yourself first?
Yes, we can see it.
Right. Thank you.
You.
Yeah. Okay. Thank you very much. Yeah. So let me get started. Okay. So next 30-40 minutes, I'm going to share about the application of reactive pyrolysis that is used for certain special type of polymer analysis, where the normal pyrolysis will not provide you a meaningful results for data interpretation. Okay. Okay, so the outline of today's webinar, we will start with a brief introduction on pyrolysis GCMS for the benefit of some of the new participants. Then we will jump into the reactive pyrolysis introduction, then some selected applications for polymer and additive analysis of different polymeric materials. Then we will conclude with the question and answer session. Okay, pyrolysis gas chromatography mass spectrometry is a hyphenated technique where pyrolyzer is attached to a GC or GCMS for the analysis of polymeric materials mainly, but it can also be used for other applications, which you will learn during this session. Okay, so as a GCMS user, you can assume, okay, that pyrolyzer is one of such a different sample introduction system, because as you know, GCMS has a different type of sample introduction devices, starting from liquid injection, gas injection, headspace analyzer, TD system, and purge and trap. So in this line, pyrolyzer is one of such additional sample introduction system that allows the GCMS to handle solid sample without any sample preparation. So that is the value that it brings to the GCMS platform. Solid sample can be analyzed directly, and also the samples which are not volatile in nature can be analyzed with this pyrolyzer, because the pyrolyzer can treat the sample at high temperature and thermally crack it to make it volatile for the analysis. If you are not a GCMS user and as a material scientist, you would definitely use a TGA as part of your material testing. So TGA provides the temperature profile of the material based on this weight loss information. So if you see the right side of this slide, where we have a data coming from evolved gas analysis mass spectrometry, the data what you get out of this evolved gas analysis also something similar to this differential thermogrammetry curve, so which ultimately tells the temperature profile of the material for additives and the polymeric compounds present in the material. So in a way, you can see that EGA-MS will produce the same data what one can get from the TGA. However, in addition to this temperature profile or the data, you can also get the chemical fingerprint of the material, because this evolved gas analysis basically collects all the chemical information through this mass spectrometry. So based on the average mass spectrum of the peak, we can easily identify or just determine the type of chemicals present in this material. So that is the additional information one can get from evolved gas analysis MS compared to the TGA. Otherwise, one has to consider a TGMS for such information. So in brief, pyrolysis GCMS is a hyphenated technique that allows to handle the solid samples directly by GCMS. The key advantage of this combination offer you the direct sample analysis, particularly for solid sample. And secondly, this pyrolyzer can be operated at high temperature. That makes even the non-volatile sample to be analyzed by GCMS by treating the sample at high temperature. So after the temperature treatment, then this sample is handled by GCMS in a normal way of any other type of analysis. Then the typical output is something similar to a chromatogram or pyrogram, from which we can really do the proper data analysis to understand the nature of the chemical or the material that we are analyzing. So within this pyrolysis GCMS, we can analyze the sample in different analytical techniques or modes. Okay, starting from this evolved gas analysis, then we can also consider thermal desorption, and also we can consider this fast pyrolysis or flash pyrolysis. And hard cut analysis is something similar to a two-dimensional analysis, where you can transfer the volatiles of different temperature zone starting from 100 to 800. Then you can produce or collect multiple data from the same sample for collecting every minute information. The fifth one is the reactive pyrolysis. In today's session, we will be talking more about the reactive pyrolysis application. So in summary, what we can say, evolved gas analysis basically is used to screen the unknown samples and find out what is there. And basically the EGA data will tell you the temperature, the thermal zone of the interest, okay, also the pyrolysis, the peak top temperature of the material for this pyrolysis. Okay, this is the basic information one can get from the evolved gas analysis. And thermal desorption is a perfect technique for a volatile analysis, including these additives. And it produces best results when we use the cryo trap, okay, the microjet cryo trap, to really collect the very, very volatile organic compounds. The hard cut technique is an outstanding method for minor component analysis, particularly in failure analysis or deformulation. Again, here the use of a microjet cryo trap and selective sampler is required to really collect these samples at different temperature zones or ranges. Okay, and pyrolysis is actually nothing but the fast pyrolysis or the flash pyrolysis, which is basically the fundamental technique for polymer identification. And FSearch is one of our software, the proprietary software that will really help you to really analyze the unknown polymer samples. The last one in this line of techniques is the reactive pyrolysis. This is considered very easy but effective technique for esters. Okay, and it simplifies the chromatogram and produce a precise and accurate data for quantification. It is excellent for additives and also the fatty acids like compounds for to analyze at like a flame, and it's also a useful approach for condensation polymer where the normal the pyrolysis data does not produce a very distinct peaks for the compound or the structural identification. So for different technique, we have to treat the sample in different manner. Okay, there are certain techniques where you have to consider a program and temperature approach or a method. So for the wall gas analysis, you do a slow heating from 100 to 800 degree. The thermal desorption also approach a similar way, but generally in low temperature range, like 100 to 300 or 350. But sometimes the EGA data can really guide you to choose this temperature range appropriate. Certain application where you can also do the thermal desorption at isothermal condition, that means heat the sample directly at this low temperature. And hot cut is basically collecting the volatiles from a different temperature ranges like 100 to 200, 200 to 300, 300 to 400, and so on and so forth. So it allows you to collect data in multiple times, whereby you are able to collect every single information which are important for failure analysis or reverse engineering application. So certain techniques or method use isothermal temperature condition. Okay, the pyrolysis or the phosphorylysis is nothing but a thermolysis, we can call it, where mostly we use single temperature condition, which can be in the range of 500 to 800. 700 or 800 is very unusual. Most of the time we will be using 500, 550 or 600 degree. Okay. In the case of reactive pyrolysis, so we add a certain reagent, okay, which we will discuss later. And basically this temperature treatment and this reagent allows to do a kind of hydrolysis and methylation. In this case, the pyrolysis is carried out at low temperature in the range of 250 to 400 degree. So high temperature definitely does not provide a good data with reactive pyrolysis. Okay, before discussing the reactive pyrolysis part in detail, I just want to give a snapshot of other methods just for the benefit of some audience who may be joining our webinar for the first time. Okay, here this slide shows a single application for the evolved gas analysis, okay, where we are trying to look at the chemical information of a ceramic composite materials used in injection molding. Okay, and the analysis is done by this evolved gas analysis, where you can see, let me turn on my, just give me a minute. Let me turn on the laser pointer. Okay, so this is the evolved gas analysis data, which is collected from 100 to 500 degree. And you can see there are multiple humps, means multiple peaks, like really indicate it has got a different group of chemicals. Okay, so with the help of our F search, we can also find out the chemicals in this EG data to some extent. So, but many instances, we cannot complete the full analysis just with evolved gas analysis. So evolved gas analysis is more like a first level of information that allows you to think of the next step to have the comprehensive information about the sample that we are trying to analyze. Okay, in this case, from the first peak, we can see the presence of this phthalates, okay, based on this ion. And secondly, the second hump is in the zone B, that shows the presence of saturated hydrocarbons. And the third one actually is like a polybutyl methacrylate. Okay, this is actually, as I said, above 350, mostly it will show the chemicals related to polymer. So that the fourth one, the fourth peak is basically indicates the presence of polystyrene. Okay, so this information you can get from FSearch as well as the GCMS like database from Wiley or NIST as well. Okay, so EGA can give the chemical information to some extent, okay, but not completely. But just to understand the benefit of EGA over TGA, okay, the TGA can only give a peak like this, but it does not provide you the chemical information, whereas the EGA must provide this chemical information to some extent. So that's the use of the EGA for material testing. The second example that I'm sharing here, actually the use of thermal desorption. Okay, thermal desorption, as I previously shown, it's mainly used for analyzing the additives present in any polymeric material. So the thermal desorption is generally done through this slow heating. Okay, 20 degree per minute is a ramp that is recommended, and temperature range can be 50 to 300 or 100 to 300 or 350, but this is a general rule of thumb to be considered for thermal desorption. So where you can see, you heat the sample at this 100 to 300 degree, then the volatiles are continuously transferred to the GC column during this desorption. Then you run a normal GCMS analysis, which provides multiple peaks to show the presence of different additives. So with the help of NIST library or the Wiley library or our F-search, we can confirm the presence of this diphromobinol or this benzene hydroxytoluene, and also this tenuine, which is actually a kind of additive, then triphenyl phosphine, also an additive, then symbolizer is trade name, then ergophos, ergonax, and so on and so forth. So the bottom line is this TD or the thermal desorption is mainly used to collect the additives information of the material. So when we want to collect the additives and polymers, then we usually go for this double shot, where the first step is to collect the additives information through thermal desorption. Then we move on to the fast pyrolysis for the polymer information. In this case, we show the data coming from a compound rubber analysis. So for the thermal desorption and pyrolysis temperature, we can use the EGA data. But if you do not want to run EGA, you can always consider the TGA data to set this temperature for thermal desorption and polymer analysis. So when we do double shot, basically you produce two set of chromatogram from one sample. So the first one provides information on the volatiles, and the second one provides information on the polymer. Okay, in this case you can say, because rubber compound will have multiple additives which are used as a coupling agent, vulcanization agent, antioxidant, and so on and so forth. So we can easily identify these compounds with the help of a NIST library as well as our FSS library. Okay. Then the polymer one, mostly we look for the monomer of different polymer. Here this sample shows the presence of isoprene and butadiene, which shows the actually the main base material of this rubber compound coming from the natural rubber. Okay, so I just tried to give a glimpse of this pyrolysis GCMS by showing certain examples where how we use the evolved gas analysis data, thermal desorption, and the fast pyrolysis. So the hard cut, something I did not take it for discussion and during today's webinar, but we may have a dedicated session for hard cut applications separately in another occasion. Okay, today the focus is to talk more about the reactive pyrolysis, which is in synonym can be called as thermally assisted hydrolysis and methylation. Okay, so this one basically a technique where we try to collect the mechanistic information of the material by performing the pyrolysis, okay, of the substrate, means the sample, together with a suitable reagent. Okay, in other words, reactive pyrolysis uses an organic alkali such as tetramethyl ammonium hydroxide and heat to hydrolyze first, then methylate the ester linkage of the material, and it produces some distinct peaks to identify the type of monomer, also different additives within the sample, so which we will understand better with some examples, classic examples. Okay, so the reactive pyrolysis, because one may have a question under what circumstance one should consider reactive pyrolysis. So reactive pyrolysis is a useful approach when you have a polymeric material with ester groups or mainly with the hydrocyclic end compounds and also for condensation polymers. So when you carry out reactive pyrolysis, you basically transfer the sample in solution or solid form to the sample cup first. Then you add this methylating reagent, and most of the time you will be using tetramethyl ammonium hydroxide to have this alkali condition. Okay, so the tetramethyl ammonium hydroxide can be diluted or dissolved in this 25% methanolic solution, and we generally use very small volume. Okay, and we allow them to dry the open air condition. Then you transfer the sample to the furnace for the reactive pyrolysis, which is actually a kind of instantaneous, because the furnace provides the temperature that is sufficient to complete the uh, reaction as well as do the pyrolysis of this methylated compound. So one can understand better with this example. Okay, here I am showing the comparison of pyrolysis, that means the standard pyrolysis or the fast pyrolysis data versus the reactive pyrolysis. Okay, we are trying to analyze the polybutylene terephthalate polymer. Okay, by both techniques, this pyrolysis and reactive pyrolysis, where we have used tetramethyl ammonium hydroxide. On the right side, you see two pyrogram. Top one coming from the flash pyrolysis carried out at 500 degrees. Okay, it shows different pyrolysates like butadiene benzoic acid, butene benzoate, and also the butynyl terephthalate and dibutynyl terephthalate. But you'll be noting that it does not shows the presence of or does not show any prominent peak for the monomer of terephthalic acid or the mono or dimethyl derivative of the butanediol. Okay, so this is what missing when you carry out the fast pyrolysis. So in this case, when you carry out the reactive pyrolysis, then it provides less number of peaks, but it provides peaks that we wanted to see to confirm the monomer of the material that we are carrying out the testing. Okay, in this case we can show the presence of this terephthalic acid in the form of dimethyl terephthalate. Similarly, for this butanediol, we can see this butylene glycol monomer ethyl and dimethoxybutane. Okay, so this is the benefit of reactive pyrolysis. When your standard pyrolysis does not provide a distinct peak for the monomer, we have to consider this reactive pyrolysis. Okay, this is another example to have a better understanding on the value of the reactive pyrolysis. Polycarbonate sometimes is cross-linked with certain reagent to really increase the melt viscosity of the material, also to increase the molecular weight for the recycling purpose. Okay, here we show the polycarbonate cross-linked with this THPE, which is nothing but tris hydroxyphenyl ethane as a cross-linking agent. Okay, so objective of this application or analysis basically to quantitate or the quantitatively analyze the THPE in a cross-linked polycarbonate. Okay, where the THPE is used for cross-linking. So as a routine, we always want to see whether a flash pyrolysis provides the information that we are looking for. Okay, when we carry out the flash pyrolysis of this cross-linked polycarbonate, so it provides a clear peak for the bisphenol A. At the same time, we do not see a very bigger peak for this THPE. But when we try to expand chromatogram of this time zone, okay, 12 to 15 minutes, we can see there are certain peaks. When we look at the extracted ion chromatogram of this THPE, also the monomer of this polycarbonate, so we can see a peak. But the problem is this shows the presence of both ions. That means we cannot confirm this is only coming from this THPE. So in this case, we have considered the reactive pyrolysis approach. So as the limitation of the first pyrolysis, the pyrolysis of polycarbonate includes ions associated with those of THPE together with PC. That means we cannot accurately determine the THPE content. Okay, so in this case, yeah, reactive pyrolysis can provide a better information or more precise information. So when you conduct reactive pyrolysis for this cross-linked polycarbonate with the TMAH, okay, it goes this hydrolysis and methylation that will provide a methylated compound for bisphenol A as well as THP. So when you analyze this by the normal pyrolysis at low temperature, so we are able to see a clear peak for this bisphenol A and a very clear peak that is for methyl this THP. Okay, so because the concentration is too small, the peak is very small, but still it can be integrated, and we have carried out 5 replicates, and consistently we were able to see the concentration closer to the same range, and the RST of these multiple replicates of number 5 shows the RST of less than 2%. So that is the level of precision one can get from this reactive pyrolysis analysis. Now we may move on with another application. Okay, in this case, we are showing the reactive pyrolysis based analysis for rapid composition and compositional analysis of liquid crystalline aromatic polyesters. Okay, so when you do a pyrolysis of these aromatic polyesters, normally it produces carboxylic acids and phenol, and the pyrolysis is also not going complete. That means there is some incomplete reaction. So you still see 50% of the solid remains at this pyrolysis. On the other hand, when we do this reactive pyrolysis, we are able to see the methyl ester of carboxylic acid and phenolic compounds. And most importantly, it does not have any residue left out. That means we are able to see the complete decomposition of the material, which is important when you are carrying out the analysis. Okay, so here again, one may ask question: what should be the reaction temperature, the pyrolysis temperature, and what is the effect of pyrolysis temperature when you do this hydrolysis and methylation? Okay, here we show the data from 3 different conditions. One is without what is called the methylating agent, TMAH, and it is carried out at standard 600 degree, where we can see only the 2 peaks, but again there are no peaks for these other compounds. Okay, then when you carry out the pyrolysis at low temperature, again without this methylating agent, it does not give any peak. That means no pyrolysis is happening, no decomposition happening. So when you have this methylating agent and do the analysis at 400 degree, then you are able to see the methyl ester derivatives of the compounds that are present in this liquid crystal polyesters. So basically, the monomethyl is coming from this para hydroxybenzoic acid methyl derivative, and the second one is coming from this terephthalic acid, and third one is coming from this bisphenol A. Okay, so this again shows the clear advantage of reactive pyrolysis on the on the analysis of this liquid crystalline polyester sample, the aromatic phase 1, compared to the flash pyrolysis. The reactive pyrolysis provide clear peaks that will help us to identify the aromatic compounds present in the liquid crystalline polymer. Okay, one can also do the composition analysis by having the known composition mixer first. Okay, in this case, we have synthesized this mixture in different composition of this terephthalic acid and parahydroxy benzene and bisphenol A. Okay, 6 different samples containing different molar ratio. Okay, and this has been analyzed and quantified. You can see in terms of the comparison of the blend composition versus the actual composition obtained from the analysis. They are almost very close in agreement. Again, you have very good reproducibility in this case also. So it's not only identifying the compounds, it can also be used for quantitation of the compounds from a different complex polymer samples like this liquid crystalline aromatic polyesters. Okay, now we move on to the fourth application. In this case, we are showing the analysis of polyethylene terephthalate as sample, where the flash pyrolysis gives the decomposition of ester groups, but there are no peaks for a monomer. So this is another example we can say similar to this PPT. So where the normal pyrolysis or the flash pyrolysis or the fast pyrolysis shows the presence of peak related to the ester groups. Okay, so vinyl benzoate, then divinyl terephthalate, also the monovinyl terephthalate, but there are no peaks related to terephthalic acid or ethylene glycol and so forth. So in this case, when you carry out reactive pyrolysis and do the pyrolysis at 400 degree, that shows the clear peaks for dimethyl ethylene glycol and monomethyl ethylene glycol and dimethyl terephthalate. So this is the benefit you can say. So certain condensation polymer, okay, where the flash pyrolysis does not provide the clear peak for the monomer, one has to consider the reactive pyrolysis technique for analyzing such materials. Okay, so again, as you know, this polyethylene terephthalate has this diethylene glycol in small quantity. So we can see the benefit of reactive pyrolysis not only for the identification but also for the quantification. Okay, so we can also do, because generally it will be in very small trace amount. So traditionally people use this hydrogenolysis, okay, and this is actually time consuming, and also the sample pre-treatment is required, and process the overall the workflow is more complicated. Compared to this, the reactive pyrolysis is very straightforward, okay, and you just have to take the sample and the methylating reagent, and we can easily get the distinct peak for this ethylene glycol origin and diethylene glycol origin. So here we show the comparison of data obtained from this reactive pyrolysis and the traditional method. Okay, so this ratio basically provides the comparison to show the agreement between the two different analytical techniques. So again, we can see the benefit of reactive pyrolysis in this case. So far I have explained the use of reactive pyrolysis for the analysis of polymer in different type of materials, where sometimes you are not able to see the monomers of the polymer by a standard fast pyrolysis technique. Now, certain additives also requires this technique or this approach, where you can have better data quality in terms of the accuracy and precision. The first example is actually the free fatty acids that is present in this styrene butadiene rubber. Okay, so again, we will show the difference of the normal thermal resorption versus the reactive pyrolysis approach. Okay, in this case, the free fatty acids, when it undergoes this hydrolysis and methylation, basically it forms it methyl esters. So it is same as this FAM analysis, you can say. Okay. So in this case, the sample preparation is very simple. You take any rubber sample. As I said, the sample can be taken as a solid itself, or sometimes you can dissolve them in certain solvent and take in small quantity. So one important point to be noted: for this reactive pyrolysis, our sample size can be as low as possible. Normally, for standard flash pyrolysis, one may take 100 microgram to 200 microgram, whereas for reactive pyrolysis, 20 to 50 microgram is already considered a good sample amount because of the sensitivity. And higher sample mass can have an incomplete reaction sometime. Okay, so smaller sample size is recommended. So once you have the sample and a methylating agent mixed in the sample cup, then it will transfer. In this case, yeah, we are using the pyrolysis temperature of 300. Then you can see the comparison of the normal thermal resorption and the reactive pyrolysis to see the value, okay, or the benefit. So in this case, although the normal thermal resorption data provide a peak for formic acid and stearic acids, but if you look very closely at the peak, okay, so there is a kind of, it's not very baseline resolved peaks. That means when you do the integration of such peaks, so your reproducibility will be something of poor. So particularly when you are analyzing certain rubber compounds where this precision is very important for this additive composition. So one has to think of a better precision method, and this is what the reactive pyrolysis basically offer. In this case, you can see again similar to the normal thermal resorption, you can have clear peak for polymer acid and stearic acid, but in the case of methyl esters. But when you zoom to these peaks, you can see this is very clearly like baseline resolved peaks. That means you can guarantee it provides high precision data compared to the normal thermal resorption analysis. Okay, in this case, we also demonstrate how reproducible. Okay, so here we have analyzed 5 times the rubber compound, okay, where we try to estimate the methyl palmitate and methyl stearate, and we can see that the overall RST is around 3.16. Okay, so this is the benefit of using the reactive pyrolysis approach compared to the normal thermal resorption for even for the additive analysis. Okay, this is another example where the precise composition analysis of industrially used natural wax, okay, where the reactive pyrolysis can provide very distinct peaks, okay, for different type of compounds present in the natural wax, starting from these fatty acids and methoxy fatty acids, alcohols, and diols. Okay, so from these peaks, okay, you can also do a quantification, okay, based on this peak area by injecting the pure standards. Then we can provide the precise data for composition of this natural wax. Okay, this is another typical example which can show the benefit of reactive pyrolysis even for the additive analysis. Okay, this is another interesting example, okay, where the free add, this is actually in pharmacopoeia, this is a non-ionic surfactant that is used, and from medical standpoint, this should not have these free fatty acids. Okay, it's a kind of regulated one in this surfactant, and the polysorbate can have these free fatty acids and bonded fatty acids. So when you want to do the fatty acids of two like states or two nature, then you have to consider a mild methylation or the hydrolysis than also the hardcore one. So whereby the hardcore one will be considered for the bonded free fatty acids, or the simple one is for the free fatty acids. So far we have shown all application where we have used tetramethyl ammonium hydroxide. So what other chemical we can use for this mild methylation or mild hydrolysis methylation? So in this case, we show the use of tetramethyl ammonium acetate for this hydrolyzing and methylating the free fatty acids. Then the same sample you take out, then again do the second stage step treatment with the tetramethyl ammonium hydroxide. So that shows a clear peaks for free fatty acids. So the first two samples, okay, shows the presence of free fatty acids in this polysorbate. The second two compounds shows, because again the peaks will be coming in the same time, but they are coming with two different treatment with two different chemicals that differentiate just the free fatty acids and bonded fatty acids. Okay, so this is also another interesting example where you can do the multi-step hydrolysis and methylation of the same sample when you are trying to look for the chemicals of different natures. Okay. So this is the last example to really wrap up this webinar. Then we can have a detailed Q&A session to answer some of the questions that may popped up in your mind during this uh, knowledge sharing. Okay. So as you know, in 3D printing applications or other application, okay, people use this photo curable resins where they have this pre-polymer and photo initiator. After that, after the application, they expose the mixer blend to the light source to have some level of cross-linking that will really stabilize this blend or the formula for longer duration. So typically what happens in this photo curing is it produces this hydroxyl, the radicals, okay, so that really leads to form this cross-linked network structure. Now, when you are having different type of photo initiator and polymer, and based on the type of application, one may want to know how this is working and how I know my material has got longer stability. So the longer stability generally based on the number of the cross-link network structure that is developed during this process. Okay, so in this case, typically the normal flash pyrolysis does not provide a distinct information. So again, we try to do tetramethyl, this ammonium hydroxide based reactive pyrolysis that provides clear peak for the photoinitiated fragment and methyl acrylic acid, then also the dimethyl derivative of this polyethylene glycol. And most importantly, we are interested to look at this cross-link network structure, which can be interpreted based on the type of methyl acrylated oligomers that are present in this sample. Okay, so generally what we see when you have these multiple like oligomers, for example, the dimer and trimer is something you do not see too much of cross-linking, but when it goes to trimer, like tetramer, pentamer, and hexamer, that really shows the number of cross-link structures that are formed in this photofluorescence. So obviously, one want to see more of this cross-link network structure for this stability of this material. So you can see the peak height, okay. So we want to see more of this tetramer, pentamer, and hexamer that will tell the more of this cross-link network structure formation in this photofluorescence. So again, this polymer processing samples also can be analyzed with the help of this reactive pyrolysis that provides very distinct information that can be used for the process optimization and product confirmation. Okay, so with that, okay, because definitely we have more than the application what we have shared in this session. So one can always visit our website frontier-lab.com and put a keyword of TMAH, and you will find more than 20-25 technical notes that shows the different type of analysis with the help of this reactive pyrolysis. Okay, to conclude this 30-40 minutes of sharing, so I want to really emphasize on few points. So reactive pyrolysis is a simple but effective technique for the analysis of polymers and additives for compounds which are difficult to be analyzed by normal pyrolysis or thermal destruction. Okay, so some cases, as I have shown, the normal pyrolysis may not give a distinct peak for certain chemicals or structural information that we are interested to verify. Okay, so this is where we have to consider this reactive pyrolysis. Okay, so in terms of the analytical performance, the reactive pyrolysis data provides a kind of high precision and high accuracy. So then question, and under what circumstance one has to consider. So in general, the reactive pyrolysis would be considered for polymer analysis, where the pyrolysis would result complex pyrogram and cannot be used for data interpretation. And reactive pyrolysis clarifies the structure of the polymer. So it applies in general to this condensation polymer and fatty acids, also the compounds with ester bonds. Okay. So mainly we have shown the application using tetramethyl ammonium hydroxide as a reagent. However, certain cases, like if you want to do a mild, okay, so like we can consider this tetramethyl ammonium acetate. In some cases, we also use this tetramethyl sulfonium hydroxide or trifluoromethylating reagent also. Okay, so it's again because tetramethyl ammonium hydroxide is the most powerful. So when you want to have a mild reaction, then you have to consider low temperature and a kind of less alkali reagent. Okay, so one important message is we have to use lower temperature for the analysis. Okay, mostly 400, yeah, 300 to 400. Then similarly, the reagent has to be appropriate to have a proper reactions. Okay, so with that, I end my presentation. Now, yeah, I'll pass it back to Asti to really lead the Q&A session. Yeah, thank you.
So much, Dr. Satterton, for that comprehensive and insightful presentation. Now we'll move into the Q&A portion of the webinar. Please continue to submit your questions in the chat box if you still have any questions, and we'll address as many as we can in the time we have. Let's dive into the first questions. Let me share my screen. Let me. Okay. Can't you see the Q&A session, Dr. Karthik?
Yes, I see it now.
Yes.
Yeah.
So we'll start with the first questions. Could you elaborate on how you perform quantifications, or do you use external calibration with individual standards? From Marco.
Yes, absolutely. Yeah. For quantification, we have to use external calibration by using individual standards and quantification based on peak area mostly than peak heights. Yeah. But for real quantification of the composition, right, we have to have the individual standards.
Okay, great. So we move to the second question, yes?
Yeah.
Okay.
Yes.
The second question is from Mandar. Do we need separate hardware for RxPy?
Yes, actually, we don't need any hardware from the instrument side. So we only need the reagent like tetramethyl ammonium hydroxide or other type of this methylating reagent. Okay, so hardware side we don't need anything special. Yes.
Okay, thank you. And then the third question. This one is kind of long. I will read it for you. Do you have any experience of analysis amine by using RxPy? We try to analyze polyurea by using TMAH at 350 degrees Celsius. However, the monomer detects as form of isocyanates. Example, HMDA shown as HMDI. Is it probably caused of the library or there is any reaction makes the amine become isocyanates? As far as I know, amine could become isocyanates by phosgenations, right, with phosgene from
Okay, so thank
Alianisky.
you. It's just like a long question. It's also a complex question, I would say. So actually, yeah, I do not have it because I do remember there is some application related to this, but the answer something I do not have in my mind. So I will definitely take your email and I will discuss with our R&D team to have some proper answer for this question. So please share your email with us. Okay, so I will definitely provide the details for you. Yeah, thank you. Yeah,
Amazing. Okay, Alianisky, you can send an email to us and then we'll answer your long questions via email. And then the next questions is from Andreas. Would reactive pyrolysis be of benefit in the analysis of nitrile butadiene rubbers and BRs and polyurethanes?
yes, absolutely. Because I can quickly recall because when we do microplastic analysis, okay, for polyurethanes, we use a TMAH as a approach, the reactive pyrolysis as a approach to really go for lower detection limits. Okay, so although you may have the flash pyrolysis, we give certain response factor. You can have more sensitive and more precise data with the reactive pyrolysis for nitrile butyl rubbers, particularly for like polyurethane. I can straight away tell yes, and for butadiene rubber, I have to check, but in principle, yes, it should provide you such data. Yeah.
Amazing. And then to the next questions. Will the slides be available after the end of the webinar, Dr.
Yes.
Karthik?
Yeah, we will be sharing the PDF format of these slides to all participants. Maybe we will only share with the participants who are interested to have it. Okay, so we do not
Okay.
want to flash it to everybody. Yeah, only so again we need a kind of short message from you that you are
Mhm.
interested to have this. This copy of this presentation.
Okay, great. Andres, you can send us an email and then we'll share the slides with you. And then to the next questions. Is this analytical technique conducted using software? From Umar Yahya.
No, actually, this is more like a manual experiment that is being done. But our setup, like auto sampler, does not have provision to add the methylating reagents through any kind of uh, syringe or so. But it can be automated. But current setup, what we have, the auto sampler can only run the samples that has already the sample and reagent. And software is only for data interpretation. It has nothing to do with the analytical technique. But maybe your question is to know whether we can really automate the addition of reagents. Yeah, it is possible, but our current setup do not have. We have to engage a third party for such operation.
Okay, great. And then for the next questions, I haven't been able to add it into the presentation, but I will read it to you from
Yeah.
the chat box. So can we for RxPy, do we need special cup to put sample?
This is normal, our deactivated cup, so you do not need our normal echo cup should do the job for you. Yeah, you don't need a special cup.
Okay, great. And then can we perform double shot analysis using RxPy method?
Actually, because if your purpose is generally for the polymer and additives, and most of the time the application that we have shared here, they are being used at 300 to 400 degree. So if your intention is to look at the additives and polymer, most likely you may have those information in one single run at like temperature like 400. So we do not see any application where we run the double shot with the reactive pyrolysis. Yeah.
Okay, great. Thank you, Dr. Karthik. And then the last questions from Andreas. They Can you share the email address to request the slide, please? You can answer. You can send it to the one, Dr. Karthik. Would you like to use the Frontier ID? And
Yeah,
then I will
yeah,
share
yeah,
it to the chat box. Okay, great.
yeah, yeah, yeah. So all can send your questions or comments to this email, okay, the Karthik at frontier-lab.ca.com. Okay. So
I
then,
will also share it
yeah,
to the
yeah,
chat box.
yeah. Please write to that email. Then we will also send the slides if you are interested. But as I said, we will send only to participants who are interested to have this copy. Okay. We do not want to fill your inbox if you are not really
Yes,
interested
of course.
to have this.
So I've sent it to the chat box, the email address that you can use. You can send us a message there. And then, okay, I think that's all of the questions, Dr. Karthik, at the
Okay,
moment.
thank you very much. I think, yeah, it went overall well, I would say. And I really appreciate the participants for taking time to join this session. I hope you got some new information or knowledge. Forward to see you again with another occasion where we may be discussing about a different topic. There are a few more topics that we want to elaborately discuss in detail, because when you try to put everything in one webinar, it's too much for the presenter as well as for the audience. So we may have this kind of dedicated session for different applications. So maybe what we have in mind is we will consider a session on UV pyrolysis GCMS application that may come in near future, maybe in 1 2 months. So that we will definitely send the announcement once everything is finalized. Yeah. So thank you, Asti Damayanti, for hosting and uh, in this webinar.
My pleasure, Dr. Karthik. And thank you so much, Dr. Karthik, for that comprehensive and insightful presentations. Thank you all for your engaging questions, and a big thank you to Dr. Karthik for sharing his expertise with us today. We hope this webinar has given you valuable insights into reactive pyrolysis and its application in polymer and additive analysis. Before we wrap up, just a quick reminder, the recording of this webinar will be shared with you soon via email. If you have any further questions or would like to learn more, feel free to reach out to us to the email address that have been sent in the chat box. And then you may also download the free technical note from the previous emails that we already sent. Thank you again for joining us, and we hope to see you at our future webinars. Have a great day. Thank you.